This is the second lecture from Chapter 6 on thermochemistry, and this lecture will focus on calorimetry, which is a method we use to measure heat exchange. We left off in the introduction to thermochemistry lecture talking about exothermic and endothermic reactions. So just a quick reminder, throughout this chapter in thermochemistry, think of yourselves as taking the position of the system, that is the molecules or atoms or chemical reaction that we're studying. So everything's kind of from the perspective of the system. So if the system during a chemical reaction gains heat, that is an endothermic process, and we talk about the heat change or thermal energy change of that system as being positive, greater than zero. So conversely, in an exothermic process, heat leaves the system, therefore leaving the system with lower energy. So the change in thermal energy, delta H, is negative in an exothermic reaction. Okay, the ultimate energy ends up lower, and therefore the change is negative. Calorimetry is the process by which scientists measure heat transfer. It can either be heat that's been absorbed by the system or heat that's been released. And this is an overly simplistic picture of a calorimeter, but basically a calorimeter is an insulated piece of equipment, hopefully not allowing any heat transferred between a system, which is here represented by S, and its surroundings, which in this case would be water, anything else it could possibly transfer heat with. So the idea is the calorimeter itself is insulated so that no heat escapes into the Wild West out in the atmosphere. Typically, since you can't usually measure the exact energy change of the system itself, it's a bunch of submicroscopic molecules, atoms, etc., you can't put a thermometer and have it measure the temperature of molecules. So typically what we do in a calorimeter is we dissolve the chemical system in water, and it's very easy to measure temperature changes of water. You just have to remember then, for example, if the temperature of the water's surroundings goes up, what does that mean? That means that the system gave away heat, okay? Or in other words, the temperature of the system, if we could measure it, would have gone down if the surroundings go up. So there's some plus and minus signs and some inverse thinking to keep straight throughout this chapter of thermochemistry. All right, so a couple of new terms to become familiar with before we start doing calorimetry calculations, and probably the most important one is specific heat capacity, which we designate with a capital C. That is a property that is unique to every single different substance, and it is a constant. It's something that has been measured and put in tables, and so you would have to be told the specific heat capacity of a material or look it up. And in very simple terms, the specific heat capacity of a substance tells us how sensitive that substance is to a change in temperature. Probably the example that you can relate to the best, when you go to a beach, if you walk across the beach itself with bare feet and it's a very hot day, your feet will start to burn. And if you're like me, you'll start running or trying to run toward the water to cool your feet off. And then when you get to the water, sometimes it's too cold. So how is it possible that at the same temperature outside, the sand becomes scalding hot and the water can actually feel cool? That's due to different heat capacities of sand versus H2O. And so I'm going to give you a little bit better feel for that, hopefully. But to get you started, here is the relationship between heat capacity and temperature sensitivity. The higher the heat capacity is for a substance, the less sensitive that substance is to temperature changes. So you'll see in a bit that water, H2O, has quite a high heat capacity. This is not working very well. It has a high heat capacity, specific heat capacity, and because of that, water is pretty resistant to temperature changes. You can shine sun on it for a long time before you're going to see a significant temperature change. On the other hand, substances that have low specific heat capacities are very sensitive to temperature changes. So can you, off the top of your head, think of a substance you know that seems to respond very quickly to temperature changes? I'm wondering if you thought of metals. You know that metals, you put them out in the hot sun, you can burn yourself real quick by touching them. On the other hand, if you put them away in the shade someplace, they can actually feel cold. So metals typically have very low specific heat capacities. Alrighty, so the units of a specific heat capacity are weird, but it's something you need to be familiar with. It just shows up here and there, and it's important to understand it. So what the units are for specific heat capacity are joules divided by grams times degrees Celsius. So what does that mean? Look at the definition for specific heat capacity and see that it lines up perfectly with those units. So specific heat capacity is the amount of heat, that's J, okay? Heat is a type of energy transfer. So joules, to raise the temperature of 1 gram of a substance, okay, here's the 1 gram, by 1 degree Celsius. And there's that. So it is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. So that's where the units come from. All right, let's look at specific heat capacities of a variety of substances just to kind of reinforce what I said a couple slides ago. So metals, the top ones are all metals, and they all have quite low specific heat capacities. Which means they're sensitive to temperature changes. That means that it doesn't take very much energy, J, to raise 1 gram of the substance by 1 degree Celsius. On the other hand, let's look at water. Wow, huh? The heat capacity, specific heat capacity of water is 4.18, an order of magnitude larger than many metals. And that means, of course, it takes quite a bit of energy, J, to raise 1 gram of water by 1 degree Celsius. Okay. This is just kind of a visual saying the same thing. You're obviously going to be tested on this concept to make sure you understand it. You could put two, even among metals, even though all metals, relatively speaking, have low specific heat capacities, of course they do differ from each other. And it turns out that gold is very much more sensitive than is aluminum to temperature changes. So think for a minute, cover up the bottom of the slide, don't look at it. Which one of these, gold or aluminum, has lower specific heat capacity? So see if you can remember what I've said the past couple slides and make that prediction. I'm hoping you have made the correlation then that as if a substance is very sensitive to temperature changes, that means its heat capacity is low. And if a substance is not very sensitive, the temperature does not change very much as it's heated, that means the heat capacity is high. So we would expect the specific heat capacity of aluminum to be quite a bit higher than the specific heat capacity of gold. All right, so here is the equation. Write it down, highlight it, set it aside someplace. You will be using it a lot. This is the equation that typically accompanies experiments run in a calorimeter. And it basically, I like to call it the MCAT equation, which may not make a lot of sense, but to me, when you shove that equation together, this is a Q, by the way, this MC delta T looks like MCAT to me, so I call it MCAT equation. Anyway, let's make sure you understand all the symbols for it. Q is heat. Remember, heat is the amount of energy transferred. M is mass in grams of the substance that's being heated. Specific heat capacity, as I said before, is capital C. And then delta T is change in temperature, which should be Celsius or Kelvin. Now, you may need to prove this to yourself, or you can just take my word for it. Even though the absolute Kelvin and Celsius are different, so if you have 100 degrees Celsius, that is 373 degrees Kelvin. So they are different. However, if you're talking about the change in temperature, delta T for Celsius is identical to delta T for Kelvin. So when you use this formula, the bottom line is you can put temperature in Kelvin or Celsius as long as it's the same. So if I'm going from 273 Kelvin down to 173 Kelvin, my delta T in Kelvin is 100 Kelvin. If you convert both of those numbers to Celsius, that would be saying if I start at 0 Celsius and let's see, 173 in Celsius is minus 100. Okay, so delta T in Celsius is 100. All right, so regardless of whether you use Celsius or Kelvin, the delta T is going to be the same. So, all right, let's try to work a couple problems with that, see how we do. One of the things that you need to keep in mind when you're doing calorimetry calculations is, as I said before, most of the time the system is put into water, and it's actually the temperature of water that is monitoring. But you need to keep in mind that water is the surroundings. It's not the system, it's the surroundings. And so whatever sign, plus or minus, you get for the temperature reading of water, you must take the opposite to understand what's happening to the system. So a way to express that mathematically is, remember, small q is heat. So whatever the heat change is for the system is equal in magnitude but opposite in sign to the heat change that has occurred to the surroundings. And if we plug in the equation I just discussed with you, so I just got done saying that the heat of the system itself, which we'll call reaction, is equal in magnitude but opposite in sign to the heat change of the surroundings. And remember, what did the MCAT equation say? It said Q equals MC delta T. So if I go ahead and plug in MC delta T for both the systems and the surroundings, I get what's shown down here. So that's mass of the system, whatever that happens to be, specific heat capacity of the system, assuming we're talking about a chemical reaction, times temperature change of the system, equals, and now you've got to put a minus sign in front of the other side of the equation, because remember that MCAT values are going to be equal in magnitude but opposite in sign. If you forget this negative sign on one side of the equation, you will get a completely different answer. So be really careful. I would make a note of it right now and highlight it. All right, so typically you will be plugging in values given to you probably all these values, but one of them will be given to you, and you'll have to solve for that one. Now it's time to introduce delta H. That is officially called enthalpy, which for our purposes, we're going to say is equivalent to heat. Enthalpy is equivalent to heat. Now, a chemist realizes that's only under certain conditions, and just to make it clear, that's only under constant pressure, but any experiments, any calculations we're going to be doing are under constant pressure. When somebody says constant pressure, it just means regular atmospheric pressure. You're not doing anything weird like pressurizing it, so it's a pretty safe bet. Anyway, so whenever you see delta H enthalpy, you can assume that it's the same thing as heat, small q. All right, so here's a sample problem, and then I've got one for you to practice on after this. All right, so in this problem, you have a metal cube of aluminum. Some of you may have done this experiment in high school chemistry. And you dump it into water, and its initial temperature of the metal cube is 45.8. That's a little bit warm. Room temperature in Celsius is around 25. And it's put into water, and the initial temperature of the water is 15 degrees. So obviously heat's going to transfer from the warmer metal cube into the water, and that heat will continue to transfer until the final temperature of the chunk of aluminum and the water will be equal. And the final temperatures of both are equal. That's called thermal equilibrium. So this is a point where you need to remember is when you're doing a calorimetry problem, the final temperature of both the systems and the surroundings are the same. That will help you simplify some of these problems. So we're talking about aluminum. The first thing you need to do, well, and water, is find the specific heat capacity for both the system, in this case is aluminum. And by the way, this is not a chemical reaction, this is a physical process, but you still use the same calculation. So the specific heat capacity of aluminum is 0.903, the specific heat capacity of water is 4.18. So let's go ahead and work through this problem. So don't get overwhelmed by this. I will walk you through it. I've just restated the question here. Here's the reaction we'll be using. Okay, MCAT on both sides, aluminum on the left side, water on the right side. Don't forget the minus sign. All right, so M stands for mass, so everything to do with aluminum has to be on the left side. So here's the mass of aluminum. Just be real careful you don't put the wrong values in. We just looked up the specific heat capacity for aluminum. We don't know what the temperature change is yet, right? We know what the original temperature is, but we don't know delta T. So let me write out to the side here. Delta anything stands for change in something. And by definition, it's the final value minus the initial value. So temperature change would be final temperature minus initial temperature. So just keep that in mind. Don't forget your minus sign. And then the mass of the water is 105.3. At this point, I'm just giving you little tidbits for future problems. Sometimes instead of a problem giving you the mass of water, they will give you the volume. So they might have said 105.3 milliliters. Some of you may remember, and if not, write it down again and memorize it, that for pure water, since the density is 1, that means that 1 gram of water equals exactly 1 milliliter. So for water, if you are given the amount in milliliters, all you have to do is cross out milliliter and put gram. Same thing for water. All right, so here's the grams of water, 105.3. Specific heat capacity of water is 4.18. And of course, we don't know delta T for water yet either. Let's go ahead and simplify the rest of the math, and then I'll show you how to handle the delta T's. So if you multiply 32 times 0.903, you get 29.348. Same thing on the right side. Don't drop that negative sign. It's tempting to do. Multiply 105.3 times 4.18. and you get 440. The next couple steps are simply just rearranging the equation, trying to get the change in temperatures isolated. And then at some point, you can do it earlier if you want. Instead of expressing delta T like this, you're going to write out what delta T stands for, like I showed you over to the right. Let me just box that in for you. It's not wanting to write for me. Okay, there we go. So remember that delta T is T final minus T initial. So that's what we've done in this step. So delta T, the change in temperature for aluminum, is the final temperature for aluminum minus the initial temperature for aluminum. Same thing for delta T for water. So final temperature of water minus the initial temperature. Now, notice the final temperature, I didn't specify final temperature of aluminum and final temperature of water. That's because the final temperature will be the same at thermal equilibrium for the water and the aluminum. Now you need to combine the final temperatures, and at this point it would probably be smart for you to go ahead and try to solve this mathematically yourself, because I think for quite a few of you, you need to kind of refresh your algebra, how you isolate equations and solve. So if you do that, you find that TF, the final temperature at thermal equilibrium for both the aluminum and water, is 17.3 degrees. So go ahead and work that up, make sure that you can get that answer too, and then I have a problem for you to work on. And here it is. This time we're going to use 20 grams of aluminum. We're going to put it in at the initial temperature. So you might want to just make a note. So here's the grams of aluminum. This is temperature initial for aluminum. 50 grams of water. Okay, so that's grams of H2O. That's our surroundings. The final temperature and is 26.5. That's a big help, right? Because that's the final temperature for both aluminum and water, right? What was the initial temperature of water? So we're solving for Ti of water. And up here it was Ti of aluminum. Specific heat capacity of aluminum, as we just said, is 0.903, and that of water is 4.18. Go ahead and work through that. What are you solving for? Okay, you're solving for the initial temperature of water, Ti of H2O. And I will go over the answer in the next page. All right, that's just the problem we stated. So this type of problem, of course, you're going to approach it like we did the sample. I'm going to say that the heat given up by the aluminum is equal to the heat gained by the water. I want to point out mathematically that it doesn't matter if you're negative, what side your negative sign is on. I could put the negative in front of QH2O, and I would still get the exact same answer. As long as you're basically, by showing that negative, you're just saying that the value on one side of the equation is the opposite of the value on the other. So you don't have to concern yourself with making sure the negative's on one side or the other. Now, just to clarify for those of you who I'm not going to confuse by saying this, remember the convention is that you use a negative for processes that are exothermic. Since the system, in this case, the aluminum, is giving away heat simply because it's hotter, you can think of that as the exothermic. And so convention would have you put a negative in front of the exothermic. But again, mathematically, it's not going to matter. So when we plug in all our values, we have 50 grams of water. Here's the specific heat capacity for water. And remember that delta T for both of them, in this case water, is is equal to T final minus T initial. Remember the problem gave us T final, okay? So T final is 26.5 degrees Celsius, and we don't know the initial temperature of water. That's what we're trying to solve for. So we'll just put TI. All right, and then on the right-hand side, you've got your negative sign. It's a 20-gram block of aluminum, specific heat capacity of aluminum, and T final is the same for both, remember? And we were given the initial temperature of the aluminum block, which is 98. So again, see if you could rearrange and solve that yourself. And the answer is right here, isn't it? There we go. The initial temperature for water is 20 degrees. Now, use some common sense, go back and see if that makes sense. If the final temperature for both was 26 degrees, that means that the original temperature of the water had to be lower than that, right? And here we go, it is. So that makes sense. So this is it for calorimetry.